Today I'll be talking about the Black-Scholes formula, some basic concepts and properties that we need to go over in order to derive the Black-Scholes formula, and then the derivation itself with a little R implementation. So the Black-Scholes formula, so let's do a little background on it. So the formula was developed by Fisher Black and Myron Scholes in 1973, hence the name Black-Scholes. And it is basically used to price call and put options. So here is the basic formula for a call option. The formula for a put option is given on the next page, which is essentially the same, just with a few sign changes. Here it is here. As you can see, it's very similar to the call option formula, but instead we have switch signs where we have a negative S0 and then a plus K, and then also the terms inside the parentheses are negative instead of positive. So here are the variables that we need to discuss first. So n is the cumulative distribution of a standard normal variable. So essentially whatever value we get within the parentheses, we take the probability of getting that value or to the left. So if you get 1 in the value, if you get 1 as the value inside the parentheses, the probability of getting 1 or to the left would be about 0.84. So that would be the value of n parentheses. And then SO is the initial price of the stock, K is the strike price, T is the amount of time till the option expires, R is the risk-free interest rate, and sigma is the volatility. So one of the concepts we have to go over first in order to understand the derivation is arbitrage. So first off, the definition of it is used to estimate the future price of an asset, such as an option price, when the future is unknown, when the future price is unknown. By doing this, we use an asset whose future price is deterministic, such as bank account amount. So using a bank account example, we can figure out the future price of the amount of money in that bank account, which is just the initial price times e to the interest rate times time. It's basic continuously compounded interest. So we'll use this later in the derivation. The next thing we have to go over is the properties of a log normal distribution, because to derive the Black-Scholes equation, we have to assume that the stock price follows a log normal distribution. So here we're going to define a variable xl, which will follow a log normal distribution. So xn would equal log of xl, that would follow a normal distribution. So using these key things and the fact that the mean of a log normal distribution is given by that function, we can proceed. So now we are going to find the partial distribution of xl, which was log normal distributed, and its mean ulk. So the mean is found by the integral from k to infinity of xl minus k times the PDF of xl, which is just the basic definition of an expected value, or mean in our case. So when you evaluate that integral, you get what is below it, which kind of looks like what we should obtain for the call option formula, but not quite. We still need to do a little more tweaking to the formula. And again, here the n is the same as what I described on the second slide, where it's the CDF of the normally distributed variable in terms, so essentially the probability to the left of our obtained value. So now to start formulating the Black-Scholes formula, we need to use arbitrage, the concept, and our log normal results on the final page, on the last page. We can substitute in the mean and standard deviation of the normally distributed variables xn and mu(n). So if we go back to the previous slide, we see that in our mean formula, we have terms that include sigma n and mu(n). So we are going to substitute the values for mu(n) and sigma n here, which we get. So now we are a little bit closer to finishing the derivation. But as you can see, the beginning part is not quite right. We should have just an SO there. And then we don't have the exponential part by the K. And we will get to that. So now we can use the arbitrage concept. So we say that our mu L K equals CERT because that mu L is our future price of our option, and then we do not know that. That is unknown to us. So we are going to use the bank account future price as sort of a, we'll use that to estimate our future option price. So we plug in CERT in place of mu LK. So if I go back 2 slides, we're going to replace the, right here, we're going to place that with C e to the RT. And then we divide both sides by e to the RT, so we obtain C by itself on the left side. And then, as you can see, we'll go back to this side. So when I divide this first part by e to the RT, it cancels this e to the RT, leaving just the SO. And then when I divide e to the RT here, I can bring it up and make it negative. And then that's how we obtain our final result. So now some R code implementation. So I did it 2 different ways. You can either code the formula yourself using just a simple function, create a simple function with the 5 outputs, or there is an R function within the option pricing package that you can download and just use. So the first way is I created a function, I created a call function, a put function, where it takes the initial price, strike price, interest rate, which is R, our time, T, and our sigma, which is our volatility. So I define D1 and D2 as the parts within the parentheses. Then I take the P norm of those, which calculates the probability to the left of our value of D1, and then times it by S, and then times it by K times the expected value of R to the T. And then I did the same exact thing for a put option, but I switched the signs and then changed, basically switched the signs, made the inside negative as well. So then I give it so here I gave it 100 for a call, 100 for the initial price, 70 for the strike price. I did 5% interest rate. I did 0.5 in terms of a year, so 6 months. And then I did 16% volatility and did the same for a put. In the upper right hand corner you see that we have 31 for a call and 0.00089 for a put. So here's a little kind of just intuitive stuff that you can tell that you could obtain from the function itself. So when our stock price SO is large, we obtain values within the parentheses, in our case D1 and D2. We obtain values that are very large, which means that the probability to the left of those values is essentially 1. So our call formula is going to reduce down to SO, our initial price, minus our strike price, times e to the negative RT, which makes our put price essentially 0. Now, when our stock price becomes small, essentially meaning the D1, D2 becomes a very large small number, the probability to the left of that would be 0. So that means our call price is going to become 0 and our put price becomes negative the initial value plus K e to the negative RT. So now using the package, we can use the package option pricing here, as you see in in quotes. Load in the package, and it gives us 2 functions, BSEC, BSEP, which is Black-Scholes European call option, Black-Scholes European price option. I give it the order was a little bit different than what I had before, but I give the same outputs, and the prices are identical to what we had on the previous 2 slides. And so there are some cons to the Black-Scholes formula. The Black-Scholes assumes that there's no risk, but people inherently stay away from risk, but there's always that slight risk involved. And the big thing is that we're assuming that stock prices follow a log normal distribution. And as you saw, the fact that we assume that is the reason why we came to our conclusion, This was the reason why we formulated the Black-Scholes formula, because of that assumption that our stock price follows log normal distribution. So if our stock price does not follow log normal distribution and that breaks down, we essentially have no reason coming up with a call and put option pricing. In other words, the PS formula just is total nonsense if our stock price does not follow a log normal distribution. And that is all. Thank you very much.